Let's see this question. In this question he is saying context-free languages and regular languages are both closed under which operation. So 4 operations are given and he is asking under which of the operations both context-free languages and regular languages are closed. First of all, we should understand what is the meaning of closure property. So closure property basically means that if you have a set, let's assume you have any set, okay, let's call it set A, and you have some operation you are applying on the elements of this set, you are applying some operation, let's call it star. So now closure property means if you take any 2 elements from this set means and you apply this operation star, so basically A star B, then this result also should belong to set A. What it means? It means basically for all A comma B belongs to A means if you take any 2 elements from this set A, okay, those elements can be same also, those elements can be different also. So if you take any 2 elements A comma B from set A and you apply this operation star, the result should also belong to set A. So then we will say that this set A, this is closed under operation star. So this is what we say, this is our closure property. Now let's see these operations. So first we will see the union of, first we will check for regular languages and we will see all these operations. So let's check union operation for regular languages. So now our base set, remember our base set is set of regular languages. So every element is a regular language. For example, this element can be phi. You know phi is a regular language. For example, this element can be sigma star. We know that sigma star is a regular language and so on. So our base set is set of regular languages. We will call it a regular set, means set of regular languages. Now this regular set, it is closed under union operation. Very easily we can prove it. If you take any 2 regular languages, let's take L1 comma L2. Let's assume both are regular languages. If they are regular languages, then what it means? It means that we have regular expression for L1, let's call it R1, and we have regular expression for L2, let's call it R2. So these are the regular expressions. These are the regular expressions. Now very easily you can see that we can make a regular expression for L1 union L2, and that regular expression will be R1 plus R2. So this is the regular expression. This plus we can also write like this, R1 R2. So both are same thing. In regular expression, either we can use this R1 plus R2. It means we are basically doing the union of language denoted by R1 and language denoted by R2. So that is the point. So you can see that if L1 and L2 are regular, then they have regular expression, and we can very easily make the regular expression for L1 union L2. So this R1 plus R2, this is the regular expression for L1 union L2, and because for L1 union L2 we have regular expression, so we can say that L1 union L2 is also regular. Hence we can say that if L1 and L2 both are regular, then their union will also be regular. So this is our, we can say that set of regular languages are closed under union operation. Let's see the second operation, that is intersection operation. So if you again, our base set is set of regular languages and they are closed under intersection operation. If you have L1, L2 both are regular languages, then very easily you can make finite automata for L1 intersection L2. And basically what we do, if L1 is regular, then we have a DFA for L1, and if L2 is regular, then we have DFA for L2. So these are the DFA. Okay. Now if you have D1 and D2, two DFA you have, both are DFA, then very easily you can make a product automata. So what you can do, you can make product automata, means you can construct D1 cross D2. This we call product automata. So this product automata will give us L1 intersection L2. So you can see that if we have D1, D2, two DFA you have, then using product automata you can construct a DFA for L1 intersection L2, and hence you can say that L1 intersection L2 is regular, because for L1 intersection L2 we have DFA. So this is the proof that set of regular languages are closed under intersection operation also. Now let's see the C operation, this concatenation. So if you have 2 regular languages L1, L2, both are regular languages, then very easily very easily we can prove that the set of regular languages are closed under concatenation. Why? See, if L1 is regular, then we have regular expression for L1. If L2 is regular, then we have regular expression for L2. Now R1 and R2, these are the regular expression for L1, L2 respectively. These are the regular expression. Now the regular expression R1 dot R2. What is this regular expression R1 dot R2? This regular expression basically denotes the language L1 concatenated with L2. So you can see that for L1 dot L2 we have regular expression R1 dot R2, and hence we can say that set of regular languages are closed under concatenation operation also, because for L1 dot L2 we have regular expression, and hence L1 dot L2 is regular. Now let's see the last operation, that is complementation operation. Set of regular languages are closed under complementation operation also. Basically, if you have L and this L is regular, let's assume L is regular language, then we know that for this L we have a DFA. Because this L is a regular language, so we have a DFA for L. Now in this from this DFA we can very easily construct a DFA for L complement. So what we do in this DFA, to construct the DFA for L complement, what we will do in this DFA D, what we are going to do, we are going to exchange the set of final state with set of non-final state. Basically what we are going to do, we are going to make all the final state, we are going to convert them into non-final state, and we are going to convert all the non-final state. If there is a non-final state in D, all the non-final state of D, we will convert them into final state. So if we do this in D, if we do this, then the resulting DFA that we will get, that DFA will accept the language L complement. So because for L complement we have constructed DFA, so we can say L complement is also regular. Hence we can say set of regular languages are closed under complementation operation also. So this is a very easy, you can say we have seen the proof of closure property of regular languages under all these four operations. And this construction is important, because this construction tells us one more in this thing. Actually, from this construction you can point down, you can note down one another important point, is that if you have a language L that is regular, then for this language L we have a minimal DFA, and let's call this minimal DFA D. So this D is the minimal DFA. Let's assume D is the minimal DFA. In this minimal DFA, let's assume we are having n state. So total n state we have, let's assume. So in the minimal DFA for L, we have n state. Now we can construct DFA for L complement. We can very easily construct the DFA for L complement using this construction. What we will do in this D, we are going to make each final state, we are going to convert each final state into non-final state, and we are going to convert every non-final state into final state. So you can see that number of states will remain the same. So you can say for L complement we will have DFA D dash, and this D dash also has n state. So this is an important point. Basically this point tells us that if L is regular and the minimal DFA has n state, then the minimal DFA for L complement will also have n state. Means minimal DFA of L, minimal DFA of L complement, both these minimal DFA will have same number of state. So this is an important result. Now let's see the closure property of CFL. So CFL are closed under union operation, and very easily we can prove it, because let's assume L1 and L2 are CFL. Let's assume they are CFL. Because L1 is CFL, so we have a CFG G1, and because L2 is CFL, so we have a CFG G2. So these are the CFG, context free grammar. Now very easily we can construct the context free grammar for L1 union L2. So let's assume that this G1 has all the variables. Let's assume this G1 has the set of non-terminal is V1, and set of terminal is your, let's assume sigma, and set of you can say the start symbol is S1, and the set of productions is P1. And let's assume this G2 has set of non-terminal V2, and this sigma is same, so set of terminal is sigma, our alphabet, and this start symbol is S2 and set of productions is P2. So without loss of generality, what we can do, we can very easily what we can do, to each variable of G1, we can add a subscript that is 1. Basically, for example, in G1, let's assume you have a variable V. Then what we will do, we will make it V1. If you have a variable A, then we will make it A1. Similarly, in G2, what we are going to do, if you have a variable A, then you will make it A2. If you have a variable V, then you will make it V2. So this is how we are going to do. So you can see this will not change anything, because all we are doing is just we are renaming the variables. Okay. So now if you have G1, G2, two context-free grammar you have for L1, L2. Now very easily you can construct the context-free grammar for L1 union L2. This is how you will do. You will add a new start symbol S, and this S will either go to S1 or it will go to S2. So we will make a new start symbol. This will either go to S1. S1 is the start symbol of G1 and S2 is the start symbol of G2. Now what we will do, we will add all the productions of G1 and we will add all the productions of G2. So now this complete grammar will be a grammar. This will be a grammar for L1 union L2, because you can see this S can either go to S1 or it can go to S2. So from this S1 we can construct all the strings of L1, and from this S2 we can construct all the strings of L2. So this is how you can see, this is the context-free grammar for L1 union L2. Hence we can say that context-free languages are closed under union operation. Okay. So now let's see intersection. So the context-free languages, the set of CFL languages, they are not closed under intersection operation. We can take a counter example for that. Let's assume L1 is A power n, B power n, C power m, where n, m greater than equal to 1. Let's assume this is your L1 and let's assume this is your L2. A power n, B power n, C power m, n, m greater than equal to 1. You can see that this L1 and this L2 both are CFL. Very easily you can see this is A power n, B power n, C power m, and this is A power n, B power m, C power m. Okay, so these are your CFL. L1 is CFL, L2 is CFL. Now what is L1 intersection L2? L1 intersection L2 is A power n, B power n, C power n, that is n greater than equal to 1. So this is a standard non-context free language. This A power n, B power n, C power n, this is a standard non-context free language. So this is your non-CFL. Hence you can say, even though L1 is CFL, L2 is CFL, but their intersection is non-CFL. Hence we can say that set of CFL, set of context free languages, are not closed under intersection operation. Let's see the next operation, that is concatenation. Set of context free languages are closed under concatenation operation, and very easily we can prove it. If you have L1, L2, two context free languages you have. Now for L1 we have a context free grammar G1, for L2 we have a context free grammar G2. The same construction we will do, we have done this type of similar construction in the union also. So this G1 and G2, these are the context free grammar. Now we can make context free grammar for L1 dot L2. How we will do? Again the same thing we will do. We will add a new start symbol, and this start symbol will go to S1 dot S2. You can see that basically this will go to S1 S2, means S1 S2. Okay, S1 S2 means basically S1 dot S2. So you can see this S1 is the start symbol of G1. This again the G1 is our V1 comma, this is set of terminals, and this is your start symbol S1, and this is set of productions. This G2 is again set of non-terminals, set of terminals, and start symbol and set of productions. So these two CFG, these two context free grammar you have. So what you can do, you can add a new start symbol S, and this S will go to S1 S2. Now again you can put all the productions of G1 and all the productions of G2. So this complete grammar, you can see this is a context free grammar, and this context free grammar will generate L1 dot L2, because S can go to S1 dot S2. Now this S1 will generate all the strings of L1 and this S2 will generate all the strings of L2. So we can say from this grammar we will generate L1 dot L2, and for L1 dot L2, because we have context free grammar, so L1 dot L2 is context free language. So this is the proof that set of context free languages are closed under concatenation operation. Let's see the complementation. Set of context free languages are not closed under complementation operation, and we can prove it very easily. We have already seen that set of CFL are closed under union, set of CFL are not closed under intersections. Now complement, okay, L complement, how can, so what we can do, we can prove that set of CFL are not closed under complementation. Okay, and how to do that? Very easily you can do that. We know that L1 intersection L2. What is this? This is nothing but L1 complement union L2 complement whole complement. So we know this if S1 and S2 two set, you have S1 S2, then S1 intersection S2. What is that? That is nothing but S1 complement union S2 complement and whole complement. Now we know that set of context free languages are not closed under intersection, and set of context free languages are already closed under union. So what we will do, we will assume that CFL are closed under complementation. We will assume this, they are closed under complementation. Okay, so if we assume this, then what will happen? If we assume this, see L1 L2 both are, we have taken them to be CFL, so L1 is CFL, L2 is CFL, and we are assuming that context free languages are closed under complementation. Then what will happen? This L1 complement, this will be CFL, L2 complement, this will be CFL. We already know that set of CFL are closed under union operation, so their union will also be CFL. Now again CFL complement, and we have assumed that CFL are closed under complementation, so this complete thing, this will also be a CFL. What we can say? We can say that L1 intersection L2 will also be a CFL. So that is a contradiction, because we have already seen that set of CFL are not closed under intersections. Okay, so but if we assume that CFL are closed under complementation, then we get a contradiction, and that contradiction is that set of CFL are closed under intersections. But this we have seen that this is not true. So hence our assumption is not true, and hence we can say set of context free languages are not closed under complementation operation. So these are your closure properties. Okay, we have seen 8 closure properties. Okay, now so what will be the answer? Answer will be union, answer will be concatenation, because regular languages and context free languages both are closed under union operation. Similarly, regular languages and context free languages both are closed under concatenation operation also. Set of CFL are not closed under intersection, set of CFL are not closed under complementation. So the answer will be option A and option C.